As we near the end of IB Physics, we're now going to look at something called nuclear fission, and it really draws upon all of the material we've been learning in previous topics. In particular, it's going to draw upon the mass defect that we discovered in E3. We'll start off our fission topic by looking at two different types of fission, spontaneous and neutron-induced. I think before we go any further, it's probably very useful to understand exactly what fission is. You'll recall in E3 that an unstable nucleus was when the strong force couldn't quite hold all of those nucleons together, and it wants to do something to become more stable. In the previous topic, the process it took to become more stable was radioactive decay, and in this topic, the process it takes to become more stable is nuclear fission. So we start with this very unstable large nucleus, and the likelihood is it's an isotope with more neutrons than protons. And there's very common isotopes that we talk about when we're talking about fission. We're usually talking about uranium-235 or plutonium-239. Of course, the examiners might come up with something weird and wonderful, but we're usually talking about these large unstable nuclei. And what they do is it splits. It splits into two smaller products. And those two smaller products are more stable. There's extra neutrons to make sure that the equation balances. We'll look at that later. And the big important thing is there's energy. And gosh, there's a lot of energy. That energy tends to come out as heat energy. And it's this energy we'll use to generate power. But what's the point of this whole slide? The point of this whole slide is to find a sentence that describes fission. And here we are. A fission reaction is where an unstable nucleus splits into smaller parts. The process often releases free neutrons and produces large amounts of energy. I need you to memorise that to explain what fission is. There's no point in me reading through this slide. You can read it just as well as I can. So I'm going to ask you to pause this tutorial and I'm going to ask you to make your own notes on the difference between spontaneous and induced fission. 2 points I think would be very important are the definitions of each and an understanding that spontaneous fission releases fewer neutrons, where induced fission releases more neutrons. One more thing, note that spontaneous fission rarely leads to a chain reaction, whereas induced fission can sustain a chain reaction, which is the basis for nuclear power and weapons. I'll leave you to note that and we'll move on to the next slide. From now on, we're going to be looking at induced fission only. And why is that? Well, induced fission is the way that we generate power in nuclear reactors, and it's the way that nuclear bombs are produced. The method of inducing fission is to take a slow neutron, and it's sometimes called a thermal neutron, and you bombard a large, already relatively unstable nucleus. And bombard, I mean we slowly direct it towards that large, relatively unstable nucleus. By introducing this slow neutron into a large, relatively unstable nucleus, we increase the ratio of neutrons to protons. And by increasing the ratio of neutrons to protons, we weaken the strong force. And by weakening the strong force, it becomes more unstable. That large, unstable nucleus then splits up and produces two fission products. These products are called daughter products, and they are more stable. I'm not saying they're completely stable because they're also highly radioactive. There's still instability in these daughter products, but not to the point where they would undergo fission. These two pairs of daughter products, you'll start to recognise them, because there's not that many of them, and some pairs are more common than others. But the more common daughter products are shown here. There are two other products of a fission reaction. The other products are neutrons, and the number of neutrons depends on the mass number of these daughter products. We'll look at that later. There's also energy. And energy is what is actually useful in this fission reaction. This graph will be very familiar to you. We looked at it in E3. And do you remember that the higher up this graph, the further up this y-axis of average binding energy per nucleon, the more stable a nucleus is. And in fact, the most stable nucleus is iron 56. If we look at uranium-235, which is a fissionable product, it's got a smaller binding energy per nucleon than iron, which means it's more unstable. It wants to become stable, so what it does is it undergoes fission, and its daughter products are usually more stable. They're higher up that y-axis, but they're still not completely there. So what they do to become more stable is they undergo radioactive decay. And remember, there are different pairs of products, and those pairs will undergo radioactive decay to become more stable. I've hinted at nuclear equations once or twice. A fission reaction is represented by balanced nuclear equation. You may have seen this if you've done chemistry before. I highly recommend you get on board with nuclear equations because you tend to be easy marks in paper 2 of IB physics. And the key to this balanced nuclear equation is that the nucleon number on this side of the equation equals the nucleon number on that side of the equation. The proton number on this side of the equation equals the proton number on that side of the equation. And previously I also said the number of neutrons released in a fission reaction really depends on the balanced equation. And you can see here that if you had 2 neutrons released in this reaction, then the equation wouldn't balance. So it has to be 3 neutrons released to make sure that this equation balances. And of course, another product is energy, but we don't really have a symbol for that in a balanced equation. Let's take some time now to draw the fission diagram. Define fission. Note the common balanced equation. I've spelt that wrong, sorry. Note the common balanced equation for a fission reaction and note the differences between spontaneous and induced fission. Head to your knowledge questions and complete question 1. I've hinted that energy is released in a nuclear fission reaction. I've hinted that that energy is what's used to create nuclear power and nuclear bombs. You need to be able to work out how much energy is released in that nuclear fission reaction. And spoiler alert, you already know. To calculate the energy released, it harks back to this idea of the mass defect and E equals mc squared. In the exam, you'd be given the mass of each of the independent parts of the balanced equation in terms of the atomic mass unit, U. And of course, what you then have to do is work out the mass defect. And once you've got the mass defect in terms of U, you'll remember that your relationship for the mass defect in terms of U and energy is 931 MeV. You'll use that relationship to work out how much energy is released in the equation. Can I remind you again that this is not in the data booklet? You need to memorise this. It's really no different to the calculation you carried out with radioactive decay, and let me prove it. Here's an example question. A nuclear fission reaction is shown below. Complete the nuclear equation for the reaction and calculate the energy released. Great, this is going to allow us to test out our balanced equation, and it's also going to allow us to calculate the energy released. Let's start with the number of nucleons. On this side, we've got 236. And on this side, we've got 137 plus 95, which gives us 232. And that means we need 4 neutrons to make that work. The proton number on this side is 92. And we've got 55 on that side so far, meaning that rubidium has 37. That's the first part of the question, a nice easy 2 marks if that's an exam. Now we need to calculate the energy released. First, we go for the mass defect. Popping that all into our calculator gives us that number of the mass defect in atomic mass units. Obviously, remembering this equation, we then multiply 931 mega electron volts by this number here, and that gives us the energy as 169 mega electron volts. That is how much energy is released in a fission reaction. Head to your revision note template and complete question 4 in knowledge questions. It's 2 pages, question 4. There's a lot there, so good luck and enjoy. I'm fighting the urge to sing. Oh, what the heck, I'm just going to go for it. I'm in the middle of a chain reaction, You're all far too young to remember this song, but it's a fabulous song. It's called Chain Reaction, and this is what this section's all about. I'm going to ask you just to look at this part of this diagram. We have a slow neutron, and that's used to induce that initial fission reaction. That fission reaction creates two daughter products, some energy, and it also creates more neutrons. Those neutrons are then used as the slow neutron for another reaction, for another unstable nucleus. And we have one final third slow neutron there. And each of those reactions then create more neutrons. It exponentially increases. And that exponential increase causes an exponential increase in the number of fission reactions. If that exponential increase in the number of reactions is uncontrolled, then it's bad. It's real bad, because what you're left with is a nuclear bomb. However, if we control that chain reaction and only use some of those neutrons to induce further fission reactions, then that controlled chain reaction is what is used in nuclear power. And that's what we're more interested in. Because don't think I'm going to be sitting here teaching you how to create a nuclear bomb. Head to your revision note template, draw a diagram of the chain reaction and explain what it is, and then complete question 2 in your knowledge questions. Let's get to the nitty-gritty of how induced fission actually creates electrical energy. It's done inside a nuclear power plant. We talked about energy from that fission reaction being released, and that energy is generally released as heat energy. What a nuclear power plant does is it harnesses that heat energy and it turns it into steam. That steam turns a turbine, and of course what we do with a turning turbine is we generate electricity. It's really very simple. It's the same as every other method of generating electricity. Steam turns a turbine and generates electricity. The only difference is the fuel that turns that turbine is nuclear fuel, and it's this containment tower and this nuclear reactor I'm very much interested in. I'm going to explain this nuclear reactor to you, and we start with the fuel rods. The fuel rods is where the uranium is, and that's where the reactions take place. Remember that we wanted to control the chain reaction and control the number of neutrons that were given out of each fission reaction to make sure that that chain reaction didn't explode too quickly. And that's what the control rods do. The control rods move up and down. You can see here. They move up and down in between the fuel rods, and they absorb excess neutrons. What that leads to is controlling the chain reaction. If they feel like the reaction's getting too fast, they move the control rods down. And if they feel like the reaction needs to speed up a little bit, they move the control rod up. Control rods are usually made from boron. Surrounding the fuel rods is something called a moderator. We're over here now. I want to just go back to that initial slow neutron going towards uranium-235. We said this was slow. If it's got greater kinetic energy, then what happens is the energy of the whole fission reaction is greater, and it can easily get out of control. So we want to control the kinetic energy of these slow neutrons. And that's what the moderator does. The moderator absorbs the kinetic energy of the neutrons to slow them down. And this is usually made out of water or carbon. And up here we have the steam generator. I want to talk about that in more detail in the next slide. The steam generator basically takes the heat from the reactor, turns the water into steam, and that steam then goes to drive the turbine. Well, we don't want contaminated water. We don't want water coming straight from that nuclear reactor into any of the rest of this nuclear power plant. It's just not safe. So the heat exchanger, or the steam generator, does just that. If you look at the fuel rods right now, follow my pen through and then up. This point here is where we're zooming into. This water here is contaminated. It's also very hot. So this water goes into the heat exchanger and it heats up a separate source of water, which is here. That separate source of water is not radioactive, but it is gleaning the heat from the contaminated hot gas and taking that heat to the turbines. Meanwhile, this stuff here is circulated back into the nuclear reactor and kept separate from the rest of the power plant. So what's the key function of the heat exchanger? It transfers heat. It takes heat from the reactor core to the secondary coolant. And it also prevents radioactive contamination by keeping the radioactive primary coolant separate from the secondary coolant. The final part of this nuclear reactor we want to talk about is keeping it safe. The shielding. The purpose of the shielding is to protect the workers and the environment from harmful radiation emitted during the nuclear fission process. We shield that nuclear reactor with different types of radiation depending on what we need to be saved from. So if we need to be saved from neutrons, then we'd use water for that. If we need to be saved from gamma rays, then we'd use lead or concrete for that. Really, each part of the nuclear reactor has different things we need to be saved from, and shielding takes that on. The shielding takes place around the reactor core and within the reactor vessel, so it's really found in areas where the radioactive material is handled or sorted. So you'll find shielding all the way through the nuclear reactor, and different shielding materials will be in different places depending on what you need at that time. Head to your revision note template, explain the role of the control rods, moderator, heat exchangers, and shielding. Those 4 things have been explicitly mentioned in the syllabus, so I suggest you know exactly what those 4 things do. Then complete question 3 in knowledge questions. For the final part of this tutorial, I am interested in the daughter products of a fission reaction. Do you remember we said they were more stable, but they were also radioactive? And you can imagine that problems will arise if you have radioactive products when you're creating nuclear fuel. What are we going to do with those radioactive products? How are we going to keep us safe? That's what I am interested in now. The nuclear fission products, there are 2 products we need to take care of. The radioactive isotopes, which are these 2, and the heat. We use most of that heat to generate electricity by creating steam and turning the turbine. But even after a nuclear reactor is shut down, fission products continue to generate a significant amount of heat for a very long time, and this is known as decay heat. So not only do we have to think about radioactive isotopes and what do we do with them, we have to think about what do we do with that extra heat. Once we finish with the fuel in a nuclear reactor, we have to think about where to put those nuclear products. And the first thing they do for a temporary amount of time is put them in water-filled pools. What that does is it reduces the heat of the nuclear fuel and it provides shielding from some of the radiation. For example, alpha radiation would be stopped by this water. Once it's cooled down, it's moved to something called a dry cask. They are large sealed containers that are air-cooled, so it's still keeping it cool, it's still just keeping it safe. And once that waste is ready for transportation, they put it onto the back of a lorry, would you believe, and they drive it to a storage site or a disposal site. This is a highly dangerous activity. After that waste is moved, it goes to something called a repository. And a repository is where we would keep nuclear waste for the long term. One of the most prominent ones is Yucca Mountain Project in America. These repositories have to be very far away from most people who live there. It has to be deep underground in stable geological formations. By that, we don't want any earthquakes. And basically, they just leave the waste there for thousands of years. Well, they don't just leave it there. There is some people there just making sure it's continuously monitored and safe. But yeah, largely they just leave that radioactive waste there. That can cause political issues. The political issues come to public opposition. Who really wants to live close to a nuclear waste site? Nobody. And also, if you're in a country that's politically unstable in the first place, or you're a smaller country that doesn't have a certain place to put your waste, then it relies on international cooperation, which is not always that easy. Very careful negotiations have to take place to ensure that one country's nuclear waste can be sent to a repository in another country. So let's do a general wind-up of the pros and cons of nuclear power. One of the biggest pros is that there's no greenhouse gas emissions. We're not burning anything. No horrible gases are going into the air. So that's a massive pro. It doesn't produce any air pollutants either. If you see steam coming out of a nuclear power plant, it's exactly that. It's steam. It's nothing else. And actually the amount of waste that's produced is very small. So the amount of waste we're taking to these repositories is tiny. Also, uranium is inexpensive. There's lots of it, and it's easier to transport, which means there's a low probability of disaster. Or is there? Because the cons are that the nuclear waste is radioactive and dangerous for years. It takes a very long time to build a power plant, and building that power plant incurs high costs and carbon dioxide emissions. Because even though there's no greenhouse gases emitted during the operation, what about while we're building it? While we're building it, a lot of carbon dioxide emissions are given off. And then we have to think about the end point of a nuclear power plant. To decommission. Decommissioning a power plant costs a lot of money. And you'll be aware that any accidents that are possible with a nuclear power plant are high profile and completely disastrous. I'm sure you've seen the Chernobyl documentaries, which has completely devastated that country and still talked about many, many years later. Head to your revision note template, go to the other notes section, and explain the issues with nuclear waste, debate the pros and cons of nuclear energy, and then complete question 5 in knowledge questions. We're finished step 1 of E5 fission. It's time to move on to step 2. See you there.